Today, I have an exciting physics experiment using a track with a funny name, Loop the Loop track. Let me play this video with 3 metal spheres rolling through this track.
Let me start with the smallest sphere. 3 to 1 go. It passed the test. Next size sphere. So far, it looks like the sphere size doesn't affect its motion. Here is the heaviest one. It did awesome. Let's watch in slow motion.
As you see, all 3 spheres completed the loop. So the point of this video is to determine the minimum height to release a sphere to complete a circular loop without falling off the track, and to prove that any sphere can successfully roll on the track when it's released from the minimal height. We are going to follow 3 steps. The first one is the conservation of energy. The second one is the Newton's second law of motion. And the third step is the acceleration for circular motion. Considering the sphere is released from the top of the track, its kinetic energy is 0. However, there is a potential energy due to the height above the ground. At the top of the loop, we have both kinetic and potential energy. The ball is above the ground, and it has speed. Now we need the potential and kinetic energy formulas. Potential energy is the mass times acceleration of gravity times the height above the ground. And kinetic energy is half of the mass times the velocity square. And we need to know the equation for the conservation of energy. The sum of the energy at the top of the track is equal to the sum of the energy at the top of the loop. Let's neglect the energy lost by friction. So here we are doing formula substitutions in the conservation of energy. The potential energy is mg height. This height is the height of released. And 0 because the kinetic energy is 0 at the top of the track. And at the top of the loop, the height is 2 times the radius. And we have kinetic energy because here we have velocity. Now we need to pause working on this equation to find the relationship for the speed of the sphere in the loop. Then we use our second step, which is the Newton's second law of motion. So as you see in this picture, the free body diagram of the weight of the sphere and the normal or contact force are both downward. By applying Newton's law equation, which states that the sum of all forces in the same orientation is equal to the product of the object mass and its acceleration. Now we add both forces, weight and normal, equal to ma. Now we need to pause this equation or in this process to find the centripetal or circular acceleration. Now we are using our third step, which is acceleration of a circular motion. So the formula is A is the speed square divided by the radius of this loop. Now back to this equation, mg plus n is equal m, and this is the substitution for A. Now we need to think about the normal force. The normal force right here at the top of this loop is 0. At this point, the centripetal force required to keep the sphere in circular motion is provided entirely by the gravitational force or the weight. So now we are going to substitute in this equation here, the normal force is 0. We can cancel mass, m, on both sides of this equation. And we have a value for the circular speed, which is the square root of g times the radius. Now let's go back to our first step, which is the conservation of energy equation, where we left, and we need to substitute now the value of the speed showing here in red. Now the square root is eliminated because speed is a square in this equation. We can go ahead and cancel mg from both sides of this equation. Now we have an expression only in terms of the height of the release and the radius of the circular loop. And finally, we have the minimum height, which is 2.5 of the radius of the circular loop. And since mass is not showing in this result, this height would work for any size sphere to complete this loop. In conclusion, the minimum height from which a sphere can be released from rest and still complete the loop without falling off is 2 times the loop's radius. Thank you for staying with me through all this tree process and demonstrating that through physics we can always calculate real values useful for practical applications.